kind of this whole clock business has turned into atomic quantum computing, right? So in a way, it evolved into that like a side branch. Did you guys run into quantum effects that you actually had to get rid of, or how come this roughly the same apparatus can be used as a quantum computer and a clock?
Yeah.
And can you just ignore the quantum effects in the clock, or how does that work? Like the quantum entanglement between the atoms and things.
Yeah, well, you can't ignore the quantum effects because it was quantum mechanics that let you do any of it in the first place. Yeah. The thing is so fundamentally quantum mechanical right from the start. I mean, the fact that atoms have energy levels is a quantum mechanical feature. I don't know if you can see it, but I'm wearing a tie that has a picture of an atom on it.
Orbitals.
Now, when I say a picture of an atom, what I mean is if someone was to ask you, draw me a picture of an atom, this is what you would draw. Right? This is the Bohr, Sommerfeld, Rutherford atom, right? Totally wrong, right? I mean, this is a completely wrong picture of an atom. It shows electrons, following orbits going around. Right. That's so wrong. The electron is in some kind of a wave function that surrounds the atom. It's not at some point and going around. And that, of course, is what we're celebrating this year, the 100th anniversary of finding out that you can't treat an atom this way, that you've got to treat an atom in a completely different way. That's what Heisenberg discovered. Schrodinger discovered a different way of thinking about it a year later and then proved that they were the same as what Heisenberg had discovered, that this idea of an orbit is just dead wrong. But it was the beginning of our quantum understanding of the way that
it's just like the intuition from the planetaries orbit.
Yeah, that's right. It was very much influenced, I think, by our understanding of the planetary model of the solar system. You think, well, the atoms must be doing the same thing. Once Rutherford understood that atoms were not a plum pudding the way Thomson thought, then, I mean, there's all these things that came together early in the 20th century. So it's not like we're trying to avoid quantum mechanics. In a sense, quantum mechanics provides
where the whole that's where the gears of the clock come from.
But
right?
By being able to do laser cooling, we can push ourselves to the quantum limits. And only when you push yourself to the quantum limits can you do things like quantum computing. Mm-hmm. So, for example, I need, if I'm going to use neutral atoms as qubits in a quantum computer, I have to know what the state of my atoms is. I can't have my atoms distributed over a whole bunch of different motional states. I better know to, as well as quantum mechanics allows me to know, where it is and what state it is. And only by laser cooling have we been able to do that for atoms, say, held in optical traps. The way, have you talked to Misha Lukin?
Yes, we did.
So he holds these atoms in optical tweezers. The thing that I was saying Steve Chu was doing next after he got the optical glasses, whereas we were doing like magnetic traps, and both things are important, right? I mean, and then we haven't even talked about the magneto-optical trap. Jean Dalibard, the one who explained, along with Claude Cohen-Tanucci, what was going on with the subdoppler cooling, invented the trap that everybody uses, the thing that revolutionized laser cooling, called the magneto-optical trap. And it's the thing, it's just magical. It gets atoms dense, cold, ready to go to the next step, where you cool them a little bit more using the polarization gradient techniques that we have, and then put it into a magnetic trap. And we haven't talked about magnetic traps, but our group was the first one to do magnetic traps. Wasn't a very good magnetic trap, but it was a start. And now you put it into good magnetic traps and you do evaporative cooling.
How does the magneto-optical trap work?
It's wonderful. So you bring in laser beams from all directions, just like with optical glasses. But now you choose a particular set of polarizations. The laser beam coming in this direction is circularly polarized. I don't remember. Well, it depends on where the magnetic field is. But they say polarized that way. The one going the opposite direction is circularly polarized the other way. Each of the pairs have pairs of opposite circular polarization. Then you put a magnetic field on. And the magnetic field is produced by what's called a quadrupole, which is what we used for our first magnetic trap. The one that I said wasn't so good, but it works beautifully here. So you put this magnetic field on, and the field is 0 at the center, and it increases linearly as you move away from the center. So the quadrupole is 2 loops of wire, but with a current going in opposite directions. So obviously, on axis in the middle, the field has to be 0 because it cancels out. But then you got these lines of magnetic field that are going like this and diverging as they come away from the coils. And so the magnetic field changes linearly. That is, it increases linearly as you move away from the center. So there's a Zeeman shift that increases linearly as you move away from the center. There's a Doppler shift that increases linearly as you change the velocity from 0. The whole thing works together. I mean, it takes a few lines on a blackboard to prove this, such that there is a force on the atom, the Doppler force that we've already talked about. It's linear in the velocity because the Doppler shift is linear in velocity. And there's a restoring force, again, because of an imbalance between the force of the 2 laser beams. That's linear in the position because of the Zeeman shift, shifting you closer to resonance with the right laser beam. So there's 2 things going on at once: a force that goes against the velocity, that's linear in the velocity, a force that goes against the position, that's linear in the position. This is what you study as a freshman in physics. It's a damped harmonic oscillator, right? You've got a force, a restoring force, that's the spring, that's linear, pushing you back toward the center, and you have a force that is linear in the velocity, that's putting the mass in an oil bath or something, right? Okay? This is what Dalibard figured out for the atoms. So you just pour atoms into this trap, and they stay. If it was a magnetic trap, you pour atoms in, and they go right back out again because there's nothing to damp their motion. Here, you pour the atoms in, and they stay. Put this on the end of a Zeeman slower, and you're just pouring atoms into these. So you get this huge number of atoms, and then you transfer them to a magnetic trap where you don't have any lasers scattering, and that way there's no more heating. You cool them down by evaporative cooling, something invented in Dan Klepner's laboratory for doing Bose condensation, which they were trying to do. So coming back to Dan Klepner, he came to me in 1976 and said, I just read this article where this guy said, you might be able to make a Bose-Einstein condensate out of a gas and hydrogen atoms. I'd like to try it. Would you like to work on this? And I said, you bet.
Well, it's like the holy grail, probably.
Yeah. And I worked on it for 2 years, didn't make much progress. 20 years later, they succeeded in getting it, and never did anything decent with it. But in the process of getting it, created the tools that allowed other people, like Eric Cornell and Carl Wyman and Wolfgang Ketterle, to do it with rubidium and with sodium. That is, Dan Klepner and his group developed the tools, the evaporative cooling, the magnetic trapping, that allowed them to the other people to do magnetic to do boson.
So evaporative cooling was already
it was in Dan Klepner's, right?
That time.
Right.
Wow.
How does evaporative cooling work? I mean, it kind of suggests
just the way
name,
you
the
think.
Name, the name
Your coffee is too hot. You blow
Yeah.
on it. What's happening when you blow on the coffee? You're getting the human
Right.
saturated air moved away, so more water can evaporate, and every water molecule that evaporates takes away more than the average energy of the water molecules that are in the coffee, and so the coffee cools down. You arrange to lose atoms from the trap.
And you just lose the high energy atoms, basically.
You arrange to lose the high energy atoms. That's part of it. The other part is what's left has to re-equilibrate and produce a new Maxwell-Boltzmann distribution of velocities. So there is another set of high energy atoms, and you can get rid of those. If the atoms don't collide and re-equilibrate, this doesn't work.
How do you lose them? What does that mean? You have like an edge. You tune it to where it's just barely trapped, or
yeah, you tune it so that the highest velocity atoms are just barely trapped, and then you let them escape.
Right.
That's one way. There's another way. You tune it so the fastest atoms are going to get to the highest value of the magnetic field, and when they get there, you use radio frequency to flip their spin energy. That's called forced evaporation.
All right, that's basically like a spatial thing. So you're separating them spatially, and then there you're kind of knocking them out.
Yeah.
Okay, interesting.
I mean, it amounts to the same thing. The highest energy atoms get to the place where they see the field that flips their spin. Alternately, they just get to the edge of the trap and spill out.
Got it.
And only the ones that are going to the highest velocity spill out. So, this has all worked together. The laser cooling, the trapping.
But this evaporative cooling doesn't really work well unless you first laser cool it, because I guess you just lose all they're too chaotic. Or
you just wouldn't be cold enough to
use the trap.
Started, yeah.
Right. Okay.
I mean, you really have to be pretty cold before you can get atoms in any kind of a trap. Mm-hmm. Neutral atoms are very hard to trap.
Right.
And before laser cooling, basically there were no traps for neutral atoms. So once, having done optical molasses, Steve Chu and his colleagues do laser trapping. Once we got laser cooled atoms, we did magnetic trapping. And the combination of those two things is used routinely all the time to make Bose-Einstein condensates.
So what's your retrospective now on this Bose-Einstein condensate experimental demonstration? So you said the ideas of implementing, like showing it experimentally, was back in 70s, and then to showing in 90s, so it was like 20, maybe more years.
So it even goes back further than that. Einstein figured it out in 1924, based on the idea that Bose had about, Bose invented quantum statistics. So based on the new idea of quantum statistics that Bose invented, Einstein figures out what we call Bose-Einstein condensation. A lot of people think Bose worked with Einstein on it. No, Bose came up with the idea of quantum statistics. Einstein took that idea and calculated Bose-Einstein condensate.
I think it would be good to explain also what is Bose-Einstein condensate.
Okay.
Just a little bit.
If you have a gas of atoms of a certain sort, namely bosons. Now, there's only two sorts of things in the world, bosons and fermions. That is, when we go to the level of atoms and subatomic particles, everything gets classified into one of two categories, bosons and fermions. And the difference is that bosons love to be together, and fermions are forbidden to be together. To be more explicit about it, it is impossible to have two particles that are the same kind, that fall into the fermion category, electrons, for example. It's impossible to have two electrons in the same quantum state. This is what leads to the Pauli exclusion principle and having chemistry and all that. But there's another class, photons are one example, that are bosons. They love to be in the same quantum state. That's why we have lasers. A whole bunch of photons in the same state. But there are certain atoms, like sodium, rubidium, that are bosons. And they love to be in the same state. And what Einstein figured out in 1924 is that if you get a gas of such atoms, cold enough and dense enough, then a phase transition happens. It's a phase transition from one kind of a gas into another kind of a gas. Start with an ordinary gas, where there's all kinds of different velocities. And then you get it cold enough and dense enough, and suddenly a whole bunch of the atoms go into the lowest possible state, which Einstein thought was stopped. That was before the Heisenberg uncertainty principle, which was 1927. And so the Heisenberg uncertainty principle says, well, they don't stop. They just go into the lowest possible quantum state available. And that's Bose-Einstein condensation. So all of a sudden, you have a huge fraction of the atoms in the lowest possible quantum state, as if it were a gas at absolute zero. But it's not, because there's a few atoms that are hanging around that are not in the lowest possible state. But this is amazing, because almost for free, you get something that's almost a gas at zero temperature. And then do all kinds of wonderful things. But then you asked another question.
In terms of the history of experimental demonstration.
So then 1976, two guys, Lou Nazanov and Bill Stwally suggest you could do this with atomic hydrogen. Because, remember the thing about forming molecules? If you make the gas dense enough, then you're going to make molecules by three-body collisions. But what they said was, if you make all the spins of the electrons of the hydrogen atom point in the same direction, then they cannot form molecules. The two hydrogen molecules where the electron spins in the same direction have no bound state. So that sounded wonderful. So Dan Kleppner goes to Tom Graytak and says, does this make any sense, this Bose-Einstein condensation, which I never heard of before? And he says, this is wonderful. And so they say, let's do it. And they come to me and say, would you start this up? So I did. I'm a postdoc now. As I said, didn't get very far. We just, but what happened in that lab after I was gone enabled Bose condensation to happen in 1995. I think it was 1998 that they finally did it with hydrogen. And hydrogen was just a long atom because it just didn't have enough collisions to re-equilibrate before something bad would happen, like a spin flip would happen, and then you get a molecule formed. That's bad. But sodium and rubidium turned out to be good in that regard. Lots of collisions before molecules would form. So, at the beginning, people thought it'll never work with rubidium or sodium because they're going to form molecules. It's only going to work with hydrogen because you can prevent molecule formation. Well, it turns out you can't prevent molecule formation in hydrogen, and you can prevent it in sodium just by getting cold enough. You see, if it's cold enough, then the density doesn't have to be high. And if the density isn't high, the chances of getting a third atom nearby when two atoms collide is very small. You're not going to make molecules.
And having the Bose-Einstein condensate, besides proving the theory, what did it turn out interesting?
Oh my gosh, did it turn out to be interesting? So here's another interesting story. When we got it, when I say we, I mean the community, it was Eric Cornell and Carl Wyman who got it first. Everybody was excited. So there was a condensed matter theorist at the University of Maryland who came to NIST. This is in Gaithersburg. The good stuff happened at NIST in Boulder. But we were all so excited, he wanted to calm us down. Basically, he was telling us, this is not interesting. Because we've already done this kind of stuff with helium on an aerogel. The density was low. We got helium basically was acting like a gas, even though it was a liquid stuck to an aerogel. And he said, and we saw, when he says we, he means the experimentalists, because he was a theorist. He saw the transition about where Einstein predicted it. So what you're doing, it really isn't interesting. So many experiments just started happening one after the other, making atom interferometers by interfering two Bose condensates, studying the interactions of the atoms and how they influenced the behavior of the trapped atoms. Just every week there was a new paper coming out with new and totally unanticipated results from these Bose condensates. So he couldn't have been more wrong about this not being interesting. It just created a whole new direction of research to the point that probably half the people doing AMO physics or more were doing Bose-Einstein condensation. And then that led to degenerate Fermi gases. So Debbie Jin, again out in Boulder, who was working with Eric Cornell to make Bose condensates, said, okay, now it's time to move on to fermions. Completely different idea, because instead of having all the atoms in the same state, you would pile up the atoms in what we call a Fermi sea. So you occupy every available energy state up to the Fermi energy with atoms now instead of electrons, and just could do all kinds of marvelous stuff. Her contribution was just so astounding.
Is there some kind of widget that can be built out of Bose-Einstein condensates, like a computer clock sensor, something like that?
Well, we're working on that. So one of the things that we're we're working on is a kind of an atom version of a squid. A squid is a superconducting quantum interference device.
Like a sensor.
It's a sensor, and it can be used as a sensor for magnetic fields.
Yeah.
And people do that. Squid magnetometers are a big deal. And it's used for all kinds of other things. It's used to make superconducting qubits for quantum computers, okay? Mm-hmm. Well, one of my colleagues, Gretchen Campbell, has made a kind of a squid out of a ring trap of atoms with a barrier. That's what a squid does. It has a tunnel barrier. It's called a Josephson junction. She made a Josephson junction in this thing so that it can detect not magnetic fields, but rotation. And this is important because if you can detect rotation better, you can make inertial navigation systems that will work better. And
this is with atoms in a vacuum?
Yeah.
Okay.
Now, we're a long way from making an inertial navigation system, but it's a first step in making devices that use atoms. It's called atomtronics, where instead of electronics, you have atomtronics. Yeah. And this is, and she made the first atomtronic circuits.